Log on, tune in, find out. Another good idea from Cambridge.
The speaker is Jan-Frederik Pietschmann. He's going to talk about identification of non-linearities in transport-diffusion models of crowded motion.
Okay, thank you very much for the introduction. I'm currently at the University of Münster, but when I started this project or started to work on this project, I was still a PhD student here in Cambridge. So I'm especially happy to be back now and be able to present that work here. Let me also mention that this is work together with Martin Burger from the University of Münster and Marie-Therese Wolfram, who actually also was here in Cambridge this term giving a lecture and is now back in Vienna. Okay, so what do I want to speak about? So in this project we considered this nonlinear drift diffusion or convection diffusion equation. So it's a rather nonlinear PDE where you have some nonlinear mobility function which depends on the density itself, and also you have some entropy function here which also is density dependent, of course, and finally you also have some given external potential. And okay, as this is a workshop with inverse problems, what we want to do is, or the aim is to somehow reconstruct or identify these two nonlinearities, the nonlinear mobility D and also the entropy functional E, while the potential is given. And we want to do this from some sort of measurements which I will make more precise later on. Okay, and of course if you set yourself this kind of problem, there's a number of questions which immediately arise, and this is also kind of the outline of my talk. So the first one is why would you want to do this? What is the reason to do this at all? To look at this rather nonlinear equation and try to do then even an inverse problem on that. The second question is, now that you set this problem, is does it make any sense at all, or is there any hope that you can really reconstruct these two functions from given measurement data? And this leads to some simple cases and some linearized versions of this equation which we looked at and which gave us, for very simple setups, some hope that this can actually be done. And finally, the last thing you want to do is what can you then really prove for the completely nonlinear inverse problem mathematically? So especially you want to probably have some uniqueness for the inverse problems. So can you prove something like identifiability for these two functions? This will roughly be the program we are looking at. Okay, so first for the motivation, let me show you two possible examples of applications that we could have. One of them is ion channel or transport in ion channels. So as most of you probably know, if you're looking at cells, then in the membrane of cells there are certain channels which regulate the influx and outflux of certain ions. For example, this is here an example of a channel which is responsible for the Ca2 plus regulation in a cell. And if the channel is rather a large one, then it can even happen that more than one ion is in the channel at a time. So that is getting a little bit crowded in the channel, and this gives rise to nonlinear models, because for linear models would not be able to capture this effect. So this is one motivation why we really want to look at completely nonlinear models, because in crowded situations it really appears here that you have some nonlinear mobility function. And the second example would be human crowd motion. While with human crowd motion I mean the motion of a large number, the collective motion of a large number of human beings, like for example in this picture, which shows the introduction of the first electric cable car in Edinburgh at the beginning of last century. And as you can see, the density of people here is also rather high, so that I can make the assumption that the movement of an individual density in this crowd is surely biased by its surrounding. So also very crowded situations, and also this motivates the need for nonlinear models in this case. Okay. So let's look at this example a little bit more closely. So from the modeling point of view in crowd motion, there's a number of difficulties. So if you compare this, for example, to physics, let's say I'm a physicist, I have this a system with many particles, for example, let's say a plasma or something like this, and there's many charged particles in this plasma. Then what I do usually is I just take two particles and look at their interaction. For example, for charged particles, I know if I just take two of them, they interact by Coulomb's law. I can calculate everything more less explicitly. And then what I want to do, if I have the system with these many particles, I want to apply some mathematical tools. And in this case, this would be a mean field limit to obtain some sort of effective equation, in this case a Vlasov equation, in which maybe I cannot say have all the information about each individual particle in the system anymore, but on the other hand I have some effective equation which tells me something about some macroscopic properties of the whole system as such. So this would be, for this case of a plasma, for example, the typical way to do it. And I mean, in terms of concepts, you basically go from something easy, from something you understand, using some mathematical tools, to something difficult. Now, on the other hand, if you look at crowd motion modeling now, the problem is, first of all, already if I have the interaction between two people, let's say you and me, it would be rather difficult because the interaction depends on many parameters, let's say, for example, age, sex, cultural heritage, and so on. But what is even more important, even if I would understand the interaction between two people very good, I cannot expect at all that if I'm in a very crowded situation that the two people, like the two of us, would behave in exactly the same way. Because actually our behavior, let's say, in a very dense crowd where panic can occur, will be fundamentally different from the behavior that the individuals had when they're just standing somewhere. So this basically tells you that for this example of crowd motion, this modeling approach going from something easy, let's say like a binary interaction, to the complex system doesn't really work anymore. And therefore the question is, what can we do to still obtain realistic models for these kind of systems? And the fact that it's not clear how to pass between these two approaches is also reflected if you look at the crowd modeling literature up to now. There are basically two approaches. The one is one approach is the microscopic approach, and there's a rather large number of microscopic models which exist. And in microscopic models, the idea is that you track each individual in the crowd as a particle. So you track every particle for himself, and then the model gives you a rule how these trajectories evolve in time. So you have, let's say, a number of n particles, and for each particle you get a law how this particle evolves in time. And on the other hand, there are microscopic models in which you don't look at individual particles anymore, but you have a density of particles, which you can, for example, think of as a probability distribution. And this gives you the probability to find a person at a time at some point in space x and some time t, and the evolution of this density is usually governed by some sort of partial differential equation. So you see that also these two things, which we had in the slide before, are reflected in the two modeling approaches, but up to now these models are purely phenomenological. So people just make up some rules and write down these models, and it's not clear what is the interaction between these two types of approaches. Okay. Now on the other hand, if you think back about the equation which I showed you in the beginning, it is clear that at least if you look at a formal point of view, you can derive this equation from from some microscopic models. For example, if you look at stochastic differential equations, or if you look at something like cellular automata, jumping processes on a lattice, and you add some size exclusion principle to that, then if you pass to the limit from these models, you can arrive at an equation which looks like this. This may not be mathematically completely rigorous, but at least formally this can be done. So this gives us at least some link between microscopic and macroscopic formulations actually, and also it gives us a relation between the microscopic and macroscopic quantities that appear here. Because of course the hope is that if I would have a macroscopic description of the system and I can measure something which might be easier in a macroscopic sense, this also tells me then back some information about the binary interaction or the interaction between smaller systems which I was looking for in the beginning. Okay, so let me show you a rather concrete example. So there are people who actually do experiments with people, and this is shown here. And what they do, I mean, from what I always said, it's quite complicated. So what they try to do, they try to look at very simple geometries. For example, this is a T-junction experiment here. They have these people, which are mostly students. They actually told me that they also made once experiments with soldiers, but actually the soldiers complained too much, so they went back to students. They are apparently easier to handle. And then they have little markers on the head, and they have cameras, stereo cameras on top, so they can track individual persons here and get trajectories. And then they just let them move. Okay, this looks like this then. And you already see one problem here, what they have. It already looks pretty crowded, but in fact the densities that these people are really interested in are much higher. So this is what you may think this is already pretty crowded, but what they are interested in is situations with much more people per square meter. And these little cells that you see here is how they try to estimate the density and the flux. So actually what they do, they draw little Vonoise cells around each of these individuals, and then they use this to calculate the density and the flux and the velocity of each people. And why do they do such an elaborated approach? Because if you look at this corridor with the people distributed somewhere like this, and I would simply put something like a square in it, and at each frame count how many people are in this square. This would give some sort of artifacts, because it can happen that if I'm unlucky, a lot of people are standing in front of this square, and then if I go one frame further, all of these people are in the square now, and if I take this square as a measurement of the density, then the density would have jumps like this, which is rather unphysical. So these people do a lot of effort to actually be able to estimate the density and the velocity from these experimental data rather closely. And still, they have the problems that they don't reach the densities, don't reach high densities as they want. So these experiments are actually done by Armin Seyfried, this guy here, who's professor in Wuppertal and also at the research center in Jülich. And the data analysis for this has been done by Jung Zhang, a PhD student of him. And what you see is that these experimentalists, what they really do, they really try to do experiments in very basic geometries with basic properties, and they try to get stuff like the fundamental diagrams of motion of human crowds. The fundamental diagram, this is the flux as a function of a velocity. And of course, the message is, if I would have a macroscopic model now, which I can calibrate with the data given from experiments, then it is rather easy to get these fundamental diagrams, for example, because the density is something that my model computes automatically. The flux can also be easily obtained from a microscopic model. And furthermore, I could do simulations if I know that the model is more or less accurate also in higher densities, in more complicated geometries, and I could get all these quantities basically for free. So this is a good motivation to try to get a microscopic accurate model by means of parameter identification. And for example, here you see one of these fundamental diagrams. So you see the flux here, given in 1/meter per second, and the density here, people per square meter. And this is the setup which is now just a corridor. And you see, for example, that if the density is very low, of course, if there's nobody, there's no flux, then the flux increases. But as soon as the density reaches some critical value, it gets so crowded that people cannot move freely anymore, and then the flux goes down again. And you see that the data, if you go to this range here where the density is higher, it's much harder to get data. So this is also reflected in the higher statistical fluctuations here. And also you see for different setups you have different results. So it's not really clear what happens in this region for high densities here. Okay. So this is why we want to look at these kind of equations. And from now on, what I will do, I will restrict myself to a stationary case. So I will only look at the stationary equation, and I will rewrite it like this. So I will introduce this function g, which is nothing else than d times e double prime, and write this in front of the gradient just to be more close to existing literature and so on. And to make this a valid problem, I also have to set this up on some bounded domain omega, let's say. And for now, I assume that the boundary of this domain is in C1, and also supplement this with Dirichlet boundary conditions, and I assume that they are H2. So I don't really care too much about regularity here. And then I have the following additional assumptions here. Okay, this is rather a long list, but let's just have a look at a few of them. So we want the mobility to be always greater or equal 0. This makes sense because it's a mobility. We want that the entropy function is convex, which is also rather common for an entropy functional. We also want that this function g here is strictly greater than 0, as long as u is strictly bounded between 0 and 1. And if you look back to the equation, this is actually something that will assure us uniform ellipticity here and will therefore be useful for the analysis as long as we choose appropriate boundary values. Okay, then we want something this here which allows us to transform to entropy variables. And also for the given potential, we just assume a very high regularity because we don't really care so much for the regularity of the potential. Okay. Now, if we have all these assumptions made, we can have a look at the direct problem. And actually, the direct problem is then just solving this equation given everything that you need. And we can prove, at least in up to 3 dimensions now, that there really exists a solution to this problem. And if we assume a linear potential, we can also prove that this solution is unique. And the strategy of proving this is rather straightforward. So what you do, you take the nonlinear equation, then you linearize it. You end up with a linear elliptic equation. For that linear elliptic equation, you can simply apply standard results. And then you use a priori bounds, which in this case are maximum principles, which you have for the linearized equations. And then by a fixed point argument, this allows you to get back to the fully nonlinear problem and show existence for the problem. Okay. Okay, now we have the direct problem set up. We have a motivation. Now the question is, do we at all have any hope that we can identify these two functions at all from some measurements? And when we first started working on this project, the first thing we looked at, we said, let's have a look at the very simple case. So we restrict ourselves to one space dimension, the domain 0, 1. We take a linear potential so that the equation reduces to this. And now we say the measurements we have are flux measurements. So assume we have given flux measurements in one space dimension, usually at the boundary, but in 1D it doesn't really matter because the flux is constant on the whole domain. Okay, and then for the reconstruction of D, the simplest case is, let's say we apply boundary conditions on both sides of this domain. Let's say we take the same value on both sides. Okay, so basically on each side of the domain have the same boundary value. Then of course the solution to this equation is constant. And if I now look at the flux which I measure, I see that this space derivative here of the constant solution is 0. So basically I can calculate d at u0, which is given by the boundary condition, basically by dividing the flux by the strength of the potential. Okay. So this tells me already that if I apply equal boundary conditions on both sides, I can at least identify the function d. Okay, now the question is, what about g? So if I now do more or less the same setup, but now instead of using the same value left and right, I add a little perturbation to one of the boundary values, so I make one of them a little larger, and then I linearize around these constant things. Then I get this linearized equation here, and I can also do the same thing. I also can have a look at the flux. This is the flux now, and if I assume that I measure this flux, then I can do some exponential transformation to get these terms together here, and then I can solve that for g. I actually get this expression here for g of u0. So this tells me that also, at least theoretical, I can get some information about g of at the position g u0. But now if you look at it from an inverse point of view, you see first of all what is needed is the information about d. Okay, that's not a problem because we just saw that we can somehow obtain this. But we see that there's a derivative here. So if d is obtained from some measurements, we have to differentiate data which probably has some noise. So there's already an inverse problem involved here. And you also see that this g of u depends on the measurements themselves and on this d prime rather nonlinear. For example, if you think of epsilon rather small, the argument of the logarithm may come close to 1, and then this is 1 over this logarithm and so on. So you see that already the ill-posedness of the problem becomes quite obvious in this rather simple approach here. But at least we can see that we can get some formula, and at least we have some hope that we can get some information from the boundary measurements. Okay. Let me also say that this also works if I add an additional function a of x here, a given function which is called area function in the context of ion channels, and which allows you also to treat 2 or 3-dimensional rotationally symmetric problems by reduction to this one-dimensional system. The only difference is that you cannot do the integration you did here anymore, and then you would have to solve some integrals numerically, but just in principle, just to say that in principle it would work in the same way. Okay, now these are 2 results which you can obtain by this simple linearization approach. You see that for d, you can reconstruct a nonlinearity pretty good. Okay, this is no surprise because we didn't do any linearization or simplification there. We just put the boundary conditions and then we get this result. On the other hand, if I want to reconstruct g here, you see already that I'm a little bit more off. And also you see, I hope you can see at least that around 0.5 the data points are even more off. And this is because if you think about the derivative of d of u is 1 minus 2u, this degenerates at this point. And then from the formula you just saw, you can imagine that this doesn't work anymore. Okay, so you may say this is not too bad, at least, considering the simple approach that we made. But on the other hand, we cheated a little here because we chose the strength of the potential rather small. So we chose u to be 0.01. And now if you think about, again, of our application like crowd motion, in crowd motion, this would be something like the typical velocity of people. So you can always assume that people, if they don't have a specific target or so, they just move with some preferred velocity. And this means especially that in this application the u will be given. So choosing that small to be closer to the linearized case is a trick which you cannot do in a fully nonlinear problem, really. So this tells us something that we can probably get some information, but it's not really suitable for practical applications. Okay, so therefore we go to the completely nonlinear inverse problem, which is basically defined as identify the functions g and d from flux measurements. Now let's say in more than one space dimension we have measured the flux over some part of the boundary of the domain, and we have the potential given and so on. And what we want to look at now is basically just flux measurements because they are the easiest to obtain for the first approach. And the first result that we can show is basically differentiability of the parameter to output map. So if you define the map tau here, which maps the nonlinearities, the potential and the boundary values to the solution u, then we can show that under rather strong regularity assumptions on g and d, so we need both of them to be C1, which especially implies that E needs to be even C3, so rather high regularity. But then we can show that this map is Fauché differentiable, and the proof to do that is rather somewhat standard. So you take the equation, think of it as some state function, some state equation, and then you use the generalized inverse function theorem. And basically you have to show that it depends continuously on all arguments, and also the derivative depends continuously on all arguments. And the main point here is that if you differentiate the state function with respect to u, you get some linearized equation here where you don't have a maximum principle anymore. So you have to work a little more to show that there exists a solution at all for this one. But this can also be done, and then you can, under these rather strong assumptions, show that regularity, that differentiability for this map is true. Okay, this is one thing. And of course, what we are interested in, we want to show identifiability. So we want to be sure that if we do this approach, that we can uniquely identify the two nonlinearities that we want to identify. And for that, we want to use the adjoint method of Du Chateau and others. And so basically, what we do, we start with two solutions corresponding to two different nonlinearities here. And of course, they have corresponding fluxes, given which are these ones. And then what you can do rather easily is you can derive an integral equality of this type. So if you look at this equality a little bit more closely, you see that you have G1 and G2 here, but both of them depend on U1. So and as we want to compare G1 and G2, it's of course a very good thing that they both depend on the same argument. Then you have the derivative of U1, okay, that's fine. And then you have also the same for D1 and D2, also both of them depend on U1. And the whole thing is multiplied by the x derivative of lambda. Okay, what is lambda now? This is, as it says, the adjoint approach. So you have some sort of adjoint equation, which is this given here. And lambda is a solution to this equation. So basically, to derive this equality, the part where you would have, at least in theory, to really work, is not to write it down like as such, but to prove that there really exists a solution to this adjoint equation. Fortunately, in our case, this is a linear, uniformly elliptic equation because this p of x can be shown to be strictly positive, and then this is also rather standard to show that there exists such a solution lambda, and therefore that this equality is valid here. Okay, and this will now be the main ingredient to actually show the identifiability of the two functions. Okay, and as a Markov, we can also show, because these p and q things here, they involve the original function u, we can show that the sign of this lambda, dx lambda, is always opposite to the sign of dxu. So for example, these two signs here would always be opposite. Okay. Now, we also need to make precise in which sense we want to prove identifiability. What we can prove actually is that both functions are not distinguishable, and distinguishability is defined as such. So you have two functions, and they are distinguishable on some interval if you know that they are not equal, of course. Okay, that's obvious. But also you ask that the difference of the two changes the sign only finitely many times on this interval. Okay, this is then some sort of additional restriction you have to make in order to be able to prove this result. And then we can prove the following theorem. So basically, if you take again the two solutions corresponding to two different nonlinearities, and you look at this interval, which is the infimum and supremum of u on the domain. Okay, it is also clear that if I want to identify d and g, I can only do this because they depend on u, on the Maxwell interval that u really takes on the domain. And then I can show that there exists a set of finitely many Dirichlet boundary conditions which I need to apply and corresponding fluxes which I can measure such that I can uniquely identify these two functions. Okay, and how does the proof work of this? So if you just look at this picture, by definition of distinguishability, we know that if these two functions were different, they would change the sign on this domain only finitely many times. So for example, in this case, they would only change the sign at these 2 points here. Okay, these points where the sign change actually really happens, I don't know how many there are, but at least I know there are finitely many ones, define some sort of partition of this interval I, which I just showed you. So for G1, G2, I get this partition in 3 parts. I can do the same thing for D. Let's say D1 and D2 also change their sign 3 times. Then I get a partition of the interval I into these 3 parts. And then I take the common refinement of these 2 ones and get that this interval is, I don't know, divided into these 5 parts. And on each of these parts, I know that the difference between G1 and G2 is rather either positive or negative, but never 0. Okay, and then what I do, I basically now I employ this integral equality which I derived earlier. So let's say I go now from interval to interval, and each interval I have to distinguish between one of these 3 cases. So either in the interval G1 is greater than G2 and D1 is greater than D2, or the other way around. Then I can choose boundary conditions such that the sign of the derivative of U1, because by maximum principle I can control the sign of the derivative of U1 with the boundary conditions is greater than zero. And then if I look at this integral equality, I know, okay, these things here, because G1 is greater than G2, I know this is positive. If D1 is also greater than D2, I also know that this is positive. Now the potential U is anyway positive. It doesn't make sense to have a negative speed here. And also by boundary conditions, I know that this one is positive. So all these terms inside here are positive, and there's no chance that they compensate each other. On the other hand, I know by derivation of this equality that this is 0, but as everything in here is positive and is added up, I know that this is greater than 0. And there I get a contradiction. Okay? So if these things would be distinguishable, then this couldn't happen here, because here's 0 and this is then greater than 0. Now if it's exactly the other way around, then I do the same thing with small equal 0 here. The second case is that G1 is smaller G2, but D1 is larger than D2. So then I could in principle have the problem that these two terms here compensate each other and still become 0. But then I have just to choose boundary conditions such a way that the derivative of U1 is now negative, and then I know that both terms are negative, and then again they cannot compensate each other, and because they have a strict sign, both of them, I can again get a contradiction. And the last but trivial case is also if I'm on it might also be possible that G1 equals G2 on an interval, but D1 is smaller or larger than D2, then then one of these two terms vanishes, but then I can still apply the same argument. Okay. So far for this identifiability proof, and then finally what we also did, we did some numerical simulations for this fully nonlinear problem, and to discretize the linear forward problem, we used mixed hybrid discontinuous Galerkin finite element method. So this means that you introduce an additional variable sigma, which equals the gradient of u, and then you solve the system of first order equations rather than solving directly the system of second order equations. And then we basically did a least squares approach. So we looked at measurements minus output operator, added some Tikhonov regularization H1, and then what we did was basically simply Landweber-Kaczmar's iteration for this system here. So we get update rules for both D and G. Okay, we have the derivative of the state function here and the solution of some adjoint function, as usual if you do Landweber. Okay, and these are one of the first results about this. So here we again try to reconstruct these two functions. And you see if the initial guess, which is rather close to the real data, but at least you can see that in the iterations you somewhat converge towards the real looked for nonlinearities. This is of course not yet so convincing yet. So what we want to do also is we know some more a priori information about these functions. For example, we know that this one here is concave. So we would also like to add this a priori information to our linearization minimization scheme, and then we hope that we can get somewhat better results. Okay, so just to conclude, what we did was we showed well-posedness of the direct problem. We looked at some linearizations in order to see whether there's at all any chance to get information about the nonlinearities from boundary measurements. And this is of course no surprise because there's a large number of literature about, for example, identification of nonlinear diffusion coefficients. But the thing is here that we want to identify mobility and entropy at the same time. We showed the Fréchet differentiability of the parameter to output map, and finally we also showed identifiability, even though only in 1D, and also we applied this Landweber-Kaczmar scheme. So what can still be done? There's still a lot to be done. We only looked at the stationary case, so the time-dependent case would be of interest. This identifiability argument, which I showed you, only works in one dimension because I'm very heavily rely on the signs of the solution of the adjoint equation, also on the sign of the solution of the primal equation. And I control these signs by means of a maximum principle, and this only works in 1D. In more than 1D, I cannot really control the sign of the gradient just by the boundary values. So I might need to go to other tools like Kahleman estimates, for example, or something like this. And also we want, as I said, to include more a priori information. And this whole thing is available as a preprint on the UCLA Chem report. Okay, and thank you for your attention.
We have time for 1 to 2 questions. Everybody?
I noted at the beginning that your equation is analogous, as it would be, to many different areas, but it's also analogous to the petroleum problem of the Buckley-Leverett equation with an additional capillary term. So your mobility term is the same as the derivative of the capillary pressure.
Okay.
and the entropy term is the same as their fractional flow.
Okay.
And there's a long literature going back at least 35, 40 years
Okay.
where they've been trying to solve this problem, even in the case where the flux functions, the various functions, are also functions of position.
Okay.
So you would
with
expect to
additional space
example,
dimension.
Yeah. So you might want to look there.
Yeah,
In
sure.
fact, Dean Oliver's book is a very good
Okay.
entry to that literature, I think. Sorry, Dean.
Okay, thank you.
Right, thanks. Thank you, Peter, again.